Well, welcome to MV Tutors. My name is Figa, and today we're doing the topic lesson of electrical circuits. As you see, I've written it over there, electrical circuits. That's what we're doing today. Now, I like to start my session with a vision. So what we are working towards is answering questions such as these. And indeed, we will answer this question at the end, but first we must learn the principles that are required in order for you to be able to answer these questions. Now, if this is what you're looking for, you came to the right place. Stick around, and by the end of this session, you would have understood everything that you need to know in grade 12. Well, let's get into it. Okay, let's start over here. Let's start with what is called actually the first law in electrical circuits, and it's called Ohm's law. Okay, it's called Ohm's law. Now, what does Ohm's law actually say? Well, according to this Ohm's law, what you need to know is basically the formula for it in its basic form. So the formula for Ohm's law that you need to know in order to define it is that potential difference is equals to the current times the resistor. So this is what you have to say in defining Ohm's law. You have to say, well, potential difference, Ohm's law says potential difference, the potential difference and potential difference is basically the voltage, okay, is, if you look at this, it's directly proportional it's directly proportional to what? Well, directly proportional to the current, which is I. Well, that's it. That's all you have to say. You can add more meat if you want to, but this is its basic understanding of Ohm's law. Now, when it comes to the formula for Ohm's law, there's usually a triangle that we do like this, where you have V on top, and then you have I there, and R on the side. So you have a triangle like that, and it's split over there and there. So this helps us because to get V, then you just say V is equals to IR. If you want to solve for current, then you would know that current is equals to V over R from the triangle. And if you want to solve the resistor, then you know it's gonna be V over I using this triangle. Okay, but you can always manipulate. It's just a manipulation of this same formula. So Ohm's law, think of this triangle over here. All right, so now what else do I want to let you know? I want you to know that the SI unit for voltage is volts, that's V, and then that for we measure current in amperes, so that's A, and then we measure resistance in ohms, like that, ohms. Okay, that you need to know as well. Okay, so this is pretty much the first principle that you need to understand. And then further than that, we need to discuss a little bit about EMF. Now, what is EMF? Okay, EMF stands for electro. Okay, that's the E. The M stands for motive, and then the F is just force, electromotive force. And the formula for EMF, therefore, let me write it in red. I'm just gonna say electromotive force, that's EMF, that's gonna be equals to, EMF is equals to the external voltage in a circuit plus the internal voltage. Okay, and remember V is IR, so you can just say I and external resistance, big R, plus I, still V, so the R this time is internal. You can think of a battery, so it's small r. That's how we write EMF. Now let me just demonstrate this to you a little bit. So what I'm going to do is that I'm going to draw, let's say we have a battery, and inside the battery you have the power source. Okay, I'll draw it like that, and then connected to it you have a small resistance. Okay, because that's the internal part of it. Okay, so you have a small linear resistance inside the battery. And just to complete my battery, let me just kind of draw it. Well, let me use a different color, so I'm gonna go too much. So that's our battery. It looks like that. Okay, so there, it's got its internal resistance and its power source moving from negative to positive. All right, and then connected to the battery. Now let's connect the battery. Okay, let's connect the battery. Let's say we are connecting the battery to a resistor as well, and the resistor that we will do is just a light bulb. Okay, inside the light bulb is a big R like this. Okay, so let me just draw my light bulb. Okay, I'll do it like that. Let's say that's the light bulb over there. Okay, so here we have big R. So can you see that then the EMF will then use this small resistance and current is flowing? Okay, so that's current over there. It's the same current that's flowing. Let's say this is closed, right? By the way, let's say this is a closed switch. Okay, so current flows from the battery and it's the same current. Okay, if it was open like this, okay, then the current will just stay there. But usually EMF, when they ask you to solve the EMF, they want you to include the closed one. But just in case they ask you for an open one, then your EMF is just going to be equals to I small r, like over there. Okay, that means there's no external resistance. Okay, so this is the formula for when it is closed. Okay, but if it's open, then EMF is equals to IR. That's if it's open. Cool. That's all I'm going to say about that. What I want us to do now is actually discuss the resistance. Okay, so we have two kinds of resistance. The one that is basically one that is in series, and we have one that's actually in parallel. Okay, so the first point of discussion, actually what I want to do is draw an example, just show you a typical example. So if we have a power source, once again, and that power source is connected to resistor 1. Resistor can be a light bulb. Okay, and then it's connected again to resistor 2 over there, like that, and then it continues like that, and then we have another resistor there, resistor 3. Okay, let's join those. Okay, so you got a power source. So that's an example of a seed resistors connected in series. They just go in one line. Okay, now those that are connected in parallel will be typically like this. There's your power source over there. Okay, and then you've got your resistor 1, and then resistor 2 like that, and then resistor 3 like that. Okay, so they are pretty much in parallel like that. Okay, and they're connected like that. It goes there, it connects there, goes down here, connects there. Okay, so there, power source connected in parallel. So these are in parallel. Okay, let me just kind of draw a line there to separate the two so that it's clear. All right, that line is 2. Okay, so that's an example of each. Now what I want us to discuss now, let's pretty much look at the remember these are in parallel. Let me just say series, parallel. What I want us to discuss though is the resistance. Okay, let's discuss the resistance themselves. Okay, the resistance. Okay, so resistance in parallel versus resistance in series. So in series, your total resistance is equals to resistance 1 plus resistance 2 plus resistance 3. You just add them up, that's it. But then your total resistance in parallel is a bit different. It's 1 over your total resistance will be equals to 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. Now to make your your total resistance under parallel resistors, what you do, there's a trick. Well, there's many tricks you could use, but the one that I prefer is the one where you say 1 divided by R1. So you open the bracket and then you say plus 1. So you pretty much write the same thing. Okay, only difference is that you have brackets. Now once you put your brackets, you put to the power minus 1. Okay, so you raise it to the power 1. That will give you your total resistance in parallel. But we will see this in practice. Just know this principle as well, this shortcut. Okay, and next I want us to look at the ammeters. Now what does the ammeter read? Ammeter reads the current. The current, and remember current is actually denoted by I. Okay, so under series, the same current I1 is equals to current 2 is equals to current 3. Now let's just check them out. Where would the current be? Now if you can imagine this to be if you can imagine these to be water pipes, and current behaves like water. So imagine the water is coming from the battery here. That same water is passing throughout all of these. Okay, so if you have an ammeter here, let's do this. If you have an ammeter here, it's ammeter 1 will be there, ammeter 2 will be there, ammeter 3 will be there. Okay, and put them in circles, put them in, if you connect an ammeter there, okay, just like that. All right, so the readings there will be such that they are all equal. Okay, now let's look at the parallel configuration. Under parallel, you will have IT, which is the total current, will be then equals to I1 plus I2 plus I3. Okay, why is that? Let's go back to our drawing over here. So remember, current acts like water. So these are water pipes. If you put water there, okay, the water is going to separate into 3 parts. So some water will get in R1 and continue, and then some will get in R2 and continue finally to R3. So they will all branch off. Okay, so if each one of these have their own ammeters, okay, ammeter, I made it green, so let's stick to green. So you'll have your A1 there, your A2, and then your A3 there. So your total, which means is that if the water comes in here, here, eventually they will come out, and over, if you have an ammeter here, you'll have an ammeter total, then it's an addition of A1, A2, and A3. Okay, because the water is coming from here. Okay, let's say it's coming from here, gets in and out, and then it meets the one that's coming out here, and then meets the one that's coming out here, and then they meet together there. Well, actually, this is the positive side, that's the negative. So flow is actually this side, it's going this way. Okay, so the current comes this way, in, out, and then it gives you a total as well. So the one leaving is equals to the one coming in, so the a total can be anywhere there. All right, okay, I hope you understood that. Okay, let's continue. And then finally, what I want us to talk about then after ammeter is actually the voltmeter. And what does the voltmeter read? It reads voltage. Simple like that. And then come here, let's see. So voltage under series, what happens to the voltage? Well, we have a total voltage, and it's equals to V1 plus V2 plus V3. Now let's go explore that, why it is like that. If we look here, okay, remember voltage is if you remember, voltage is equals to IR, right? So each one of them has a different R. The I is the same in all of them. Remember, we spoke about the current, it's the same current, but the resistors are different. They might not be the same, are different. So thus then we will have a total voltage over here. Okay, so we'll have to add them up. Right, now let's look at parallel, the voltmeter, a voltage under parallel conditions. Under parallel conditions, we have such that V1 is equals to V2 is equals to V3. Now let's go explore why that is. Now like I said, voltage is equals to IR. The I is not the same, but it's in proportion. Okay, so if these are the same resistors, all of them are like 1 ohms each, then the IR, they'll take a third of current. But then because they're also the same, the R's are the same, so all of them have the same I. Okay, all of them have the same I, and then all of them have the same R, so then they will be equal. The voltages in each will be equal. I hope that makes sense to you. Keep this in mind. We will come back to these principles when we answer the questions, because they're very important to understand. They will help you answer the questions. But let us actually move on right now. Let's talk a little bit about electrical energy. Okay, electrical energy. And really, when we are talking about electrical energy, we're talking about power. Okay, so power is just the rate at which work is done. If they ask you definition of power, it's the rate. So rate, remember, rate has to do with change in time, dividing with change in time, and is the rate of what? Of work done. So it's like that. Power is equals to W over T. So if I'm to isolate the W, which is work done, is just equals to power times change in time. That's it. But also, if you look at your formula sheet, and based on electrical circuits, power is equals to VI, voltage times current. Okay, another formula, instead of voltage times current, it's current squared, okay, times resistance, if you have resistance. But also a third one that we could look at is that power is equals to voltage squared over R. Okay, so how do you choose which one to use of these four? You choose the one that is relevant. So based on what you are looking for, and based on what you have or what you've been given. So if you've been given voltage and current, you'll use this first one. If you have current and resistance, you'll use a second one. If you have voltage and resistance, you'll use this third one. Now, when it comes to work as well, we can then say, remember, it's power times change in time. So power on this first one is VI, and then you put the change in time. The next one, the power is I squared R, and then you put the change in time. Then the last one is V squared over R, and then you put your change in time. Which one you choose? The most relevant one, based on what you have and what you have to solve. Now, one last principle that I want us to learn is that which talks about bulb brightness. How do you make a bulb brighter? Okay, bulb brightness. Sometimes they want you to know this in metric. The one thing that you need to know is that an increase in power makes an increase in bulb brightness, right? There we go. An increase in power is an increase in in a bulb brightness. So what we are trying to do here is just increase the power, but we're given series, and we also have, you know, parallel. So how do you make the bulbs brighter? So in series, okay, I'll write a sentence here. The power is actually proportional to resistance. Okay, it's directly proportional. Directly proportional. So what does this mean for us? That means, how can I increase power if I want the bulbs to be brighter? This means that an increase, so you need to increase resistance. You need to increase resistance, and increasing resistance increases power. Or let me just say, to increase power. All right, increase resistance to increase power. Okay, and that increase in power, you know, makes it brighter, makes bulb brighter. Okay, but now what if we're in parallels? So in parallel, actually it's like this. The power is inversely proportional to resistance. Okay, inversely proportional. So then how do we make power increase if resistance is inversely proportional? Just give myself more space. That means we need to decrease resistance in order to increase power, because the whole thing is about increasing the power, right? So we need to decrease resistance, and that will make bulb brighter. Okay, so sometimes they can ask you in the exam, these resistors are connected in series or in parallel. If they're connected in parallel, how can we increase the brightness of the bulb? So all you have to say is that, well, in parallel conditions, the resistance is inversely proportional. So in order to make the bulb brighter, you need to decrease the resistance, and decreasing the resistance will make the power increase. Okay, now these are all the principles that we need to learn in order for us to answer the question. Now I think we can go and answer the question. Okay, let's just check it out real quick. Okay, so all of these are the principles that we have basically gone through. Okay, now let's come back to the actual questions that we need to answer, right? So that we good. So here, let's read this together. What's happening here? Okay, let me give myself more space. Let's start there. So in the circuit below, okay, in the circuit diagram below, the battery has an unknown EMF and an internal resistance of 0.8. So this is a battery over here. We have a battery over here. Okay, it's got its internal resistance of 0.8, and it makes the current is flowing from this side to that side. State Ohm's law. Well, we spoke about Ohm's law this side. Okay, we said its potential difference is directly proportional to the current. Okay, so just we can refer back to that. But what I want are these questions over here. It said the reading on ammeter A2. Where's A2? Oh, it's over there. It's connected to the resistance of 4. Is 0.6 amperes. The switch S is closed, so that means current is actually flowing throughout. Okay, now calculate the reading on voltmeter 1. Where's voltmeter 1? Voltmeter 1 is over there. So remember, okay, let's do that. Let me do this. 9.1.2. So V1, so voltmeter is equals to what? IR, remember? And what's the current that's flowing? Okay, so the current that's flowing, we've been where's V1? V1 is there, so it's like the voltmeter between both of these. Okay, so the current that's flowing there, we've been given, is 0.6 times what is the resistance? Okay, the resistance, I think it's just considering this 4, so we'll just consider that 4. This voltmeter is connected to this 4. Okay, so it's just 0.6 times 4. Let's bring out a calculator, and then we'll put 0.6 times 4, and then we get, okay, let's put that 2.4. So 2.4, and what's that? That's the SI unit for voltage. It's just volts. All right, now let's go to the next question, which is 9.1.3. the current through the 6 ohm resistor. Okay, so first of all, what is current? If you remember, even just based on the Ohm's law, it's I is equals to V over R, or you can draw the triangle, you'll see that is V over R. Okay, so now what is our voltage? Now remember, these are connected in parallel. What did we say about voltage in parallel? Let's go look at our table. We spoke about it over here. We said voltage in parallel there, V1 is equals to V2 is equals to V3. So voltage in each one of them is exactly the same. Okay, so that's all we have to remember. So our voltage then over here is exactly the same as the voltage on the 4 ohms one. So the voltage is 2.4 volts divided by the resistor of 6. So this is what we need to put in the calculator. So now we have 2.4, when I say 24, it's 2.4 divided by 0.6, like that. What's wrong with me? It's not 0.6, it's divided by 6, and I get 0.4. What is the SI unit for current? Amps, amperes. Okay, there we go. Let's go to the next one, which is 9.1. all right, let's go green. It's 9.1.4. okay, the reading on the voltmeter V2. Where's V2? So the voltmeter there, remember, first of all, voltmeter, volts is equals to I times R. So what is our current over there? Okay, so first of all, we've got current that is actually flowing over here. We just calculated current on the, and remember, if it's water, remember I said water, it's coming here, all right, and then it's coming here as well. All right, so what we're gonna do then is that we've calculated the water that's coming into the 6 ohms one. Now we need the current that's coming into the 4 ohms, and we have it as 0.6, and the water that's coming out here is like the total current. So it's gonna be the 6 ohms one that's gonna come out here first. It's gonna be 0.4, which is this 0.4 current that we just calculated, and then it will be joined by this one here of 0.6. 0.6, that's the current coming from the resistor of 4 ohms. So it will join, so we have to add those currents, and then as it reaches here, those currents, those total currents, then we multiply them with the resistor of 5.8 that is given over there. Okay, let me bring out the calculator. So really here then we'll put it exactly like that. Open bracket 0.4 plus 0.6, close that bracket, and then we multiply it by 5.8. Okay, 29, let's put in decimal, so we get 5.8. and then what is the SI units for voltage? It is volts, like that. Cool. All right, so that's why I was saying think of current as something that's flowing, water that is flowing in a pipeline, and these are just pipelines. So practically what's happening, that's exactly what's happening. Current flows like water in a pipe. Okay, let's look at 9.1.5 now. So they want the EMF. Okay, now we know that EMF is actually equals to, let me write that last, it's actually equals to V external voltage plus the internal voltage. Okay, now V is equals to IR, so it's I big R plus the internal one is the same I, but the R is a small r. Okay, so now in order for us to solve the big big R, remember big R, now we have these which are connected in series, in parallel, and then we have plus this one connected in series. How did I say we add up those that are connected, the resistors that are connected in parallel? I gave you a formula right over here. Let's go check it out, because we need that principle right about now. Where did I write it? Oh yeah, over there. I said you add them up, put them in a bracket, and put -1. Okay, so that's exactly what we are going to do. Okay, so I want us to actually solve the total R here. Okay, so that will add to this one, but let's start with the R parallel. So we will say R parallel is equals to brackets 1 over let me do this, 1 over 6 plus 1 over 4. I close that bracket and I say -1. Okay, let me put that in a calculator then. Let's move our calculator this side. So I said open bracket, it's 1 divided by 6 plus 1 divided by 4, close that bracket, to the power -1, and that's equals to 12 over 4, 2.4. See, you get 2.4 ohms. That's parallel. But now to get R total, which is the big R, we must say R parallel plus R, the one that's in series, which is this one. And for that, R parallel is 2.4 plus R series is 5.8. Okay, let's put that in a calculator. 2.4 plus 5.8, which is in series, and then we get 8.2. Thank you. So 8.2 is our total R. So that's big R. Okay, so current, total current, we already know total current is 0.4 plus 0.6, which is just 1. So we've got 1 there, and total R is 8.2, so we got 8.2 plus total current again is just 1, and then the internal resistance of the battery, small r, is 0.8 over there. Okay, you see it, 0.8 as given. So we'll put our 0.8 over there, and then it's just 8.2 plus 0.8. Let's put that in a calculator. So it's 8.2 plus 0.8, we get 9. So it's 9, and EMF is measured in volts because it's volts external plus volts internal. All right, so that's our answer there, 9.1.5. Okay, so that's it. Let's check out the next question, which is 9.1.6. Energy dissipated as heat inside the battery if the current flows in the circuit for 15 seconds. So energy is just work done. If you think of it, when you're working, man, you're spending energy. So work done is energy. And remember, we said the formula for work done, we discussed it over here. There we go. It's just P times change in T. So let's take this second formula over here, VI, and then change in T. So we're gonna say VI and then change in T. Cool. Now, what is this voltage that we are talking about? Come, let's read the question. Energy dissipated as heat inside the battery. So we're talking about the battery. And then what's the voltage of the that's inside the battery? I mean, not the voltage, the resistance. Okay, or the voltage inside the battery, because that's what we need. The voltage is equals to IR inside the battery here. You see, voltage is IR. The I was 1 and the R is 0.8. So our voltage is 0.8. And then what's our current? Our current is just 1. And then what's our change in time? Let's come back to the question. Flows in the circuit for 15 seconds. Time always has to be in seconds. So if the question gives you in minutes, convert it to seconds. All right, so 0.8 times 1 times 15, and that gives you 12. And then what is the measurements of work done? Work done is given, energy is given in joules. Okay, so that's our final answer over there. Well, that's it. Well, you could have actually used any of these formulas and any of them would have given you the exact same answer using any of those variables that we have. If you said I squared, our I squared is 1, and then small resistance is 0.8 times 15 gives you the same answer. Voltage 0.8 squared over R, 0.8, and it's still going to give you the same answer of 12. Okay, well, I think that's it. Well, in the event that you didn't understand anything or you need further explanation, do contact me. I would love to be your tutor. Contact me on MV Tutors, my website, www.mvtutors.co.za, or alternatively you can WhatsApp me on 076-312-1107, and I'll be happy to assist you. But please, before you do contact us, do contact me, please speak to your parent or your guardian, because remember, at the end of the day, they are the ones that will be paying for your tutoring services. Okay, so they need to be involved in the process. Other than that, I hope you understood, and I do appreciate you. Thank you.